everyone. This is the first lecture of week 11. Recall that the last few lectures of week 10 we were learning about affine scaling method. Okay. So, yeah, we learnt what the steps of the algorithm was, and we also looked at one example where the feasible set was a triangle with vertices 0 0, 1 0 and half half, right. So, I will work out a few more examples in this lecture. One reason I want to work out as many examples as possible, specifically for constraint optimization, you might have observed in the last few weeks, I am spending time working out more and more examples, say, rather than covering more algorithms, right. So, the reason is that you can see that the code for each of the method is much more complicated than the codes for constraint optimization, right. So, I would like to take as many examples as possible, so that you are clear about what is going on in the method, what is the algorithm, and how things work out in each of the method, right. So, I will spend this lecture working out examples, and then we will move to the next method in the next lecture. Okay. Fine. So, recall that the first example that we worked out in the previous lecture was the same example, same old example which we are mulling over for quite some time now. Okay. And the feasible set is something that we were we have started with, I think, when we started the quadratic penalty method, right. So, and we saw that the trajectory was in the interior, right. So, we did some modifications of the objective function and the initial point, right. So, we saw that the trajectory was completely in the interior, right. So, the reason for that is nothing but recall that our projection is taking care of, we are taking the steepest descent direction and projecting it onto the null space of A, right. So, that is taking care that we are not moving out of the set at any point, and I mean, we are not even moving near the boundary, right. So, somehow we are, I mean, pushed to the interior by the centering decentering process and so on. Okay. All right, so let us work out the next example. Okay. So, let us say we minimize C transpose x subject to the conditions that x1 plus x2 less than or equal to 1 and 2x1 plus 4x2 less than or equal to 3, x1 x2 greater than or equal to 0. Okay. So, it is good to draw, because this is in 2 dimensions, right. So, let us understand how this feasible set looks like. Okay. So, we will have, so x1 x2 and x1 plus x2 less than or equal to 1 will be here. So, this will be 1 comma 0 and this is 0 comma 1. Okay. 2x1 plus 4x2 less than or equal to 3 is, so it starts with 3 by 4 here and ends at 3 by 2 here, right. So, roughly this. Okay. So, the feasible set is, right. So, it is a quadrilateral. Okay. I think I worked out this example sometime before, but nevertheless I am just recalling this, and the intersection point is half comma half, right. So, half plus half is 1 and 1 plus 2 is 3, right. So, as simple as that. Okay. And you have 4 vertices here, 0 1, 1 0, 0 0 and half comma half, that is the reason I said it is a quadrilateral, right. And now we will modify this into its standard form, capital Ax is equal to b, right. So, if you do that, you will have x1 plus x2 plus x3 will be 1 and 2x1 plus 4x2 plus x4 will be 3, and you also need to add x4 non-negative and x3 non-negative and x4 non-negative, right. So, yeah, this is just a 2 cross 4 matrix. So, you have A is 1 1 1 0, 2 4 0 1, okay, and B is 1 3, and yeah, C we will figure, I mean we can change it as we please, okay. So, we will do that, and so something I want you to note as far as C is concerned is that, yeah, so suppose I put yeah, C is say minus 1 minus 1, okay. So, I mean you know how to find the answer without going through any of the steps, you just I mean given that we have the geometry, right. So, you can just substitute C transpose x and check which is giving you the minimum. So, this gives you 0, this gives you minus 1, this gives you minus 1, this also gives you minus 1, right. So, oh I am sorry, yes, 0 comma 1 is not the, yeah, 0 comma 1 is for this. So, yeah, the 0 comma 3 by 4, yeah, 0 comma 3 by 4 is the corner point. So, yeah, please correct this and yeah, keep the corrected vertex in mind, okay. So, yeah, so you have 0, minus 3 by 4, minus 1 and minus 1. So, both of these points half comma half and 1 comma 0, in fact all of these points here, right. So, that will minimize, right. So, in this case x star is, you can say, I mean it is actually all of this line, but since this will always converge to a vector, sorry, converge to the vertex, right. So, it is both of these, right. So, if you have, yeah, something less than 1, less than, sorry, I should say greater than minus 1, okay. In such a case you will see that yeah, so it's only 1 comma 0, right, because so here you will have minus 1, here you will have something less than minus 1, and here anyway it is less than sorry greater than minus 1, and here also it will be greater than minus 1. So, it is 1 comma 0, and if it is, so yeah, another thing that I should mention is yeah, so let me put minus 2, okay. So, yeah, in this case you can see that, so you have minus half, this is minus 3 point, sorry minus 3 by 2, right, and here as well it is minus 3 by 2. So, it is all of the line segments joining 0 comma 3 by 4 and half comma half, I mean all points are minimizers, but if you consider only the vertex, it is half comma half and 0 comma 3 by 4, okay. So, what this means is that if you have minus 1 t in the interval minus 2 comma minus 1, then x star is just half comma half, and if t is less than minus 2, then x star is 0 3 by 4, okay. Verifying this is not very hard, okay. So, you can do that, and yeah, of course, you can scale this as well. So, if yeah, the first one is minus 1 and the second one, that is C1 is minus 1 and C2 is any possible t, right. So, I have told you what the solutions are going to be, okay. So, yeah, so why I have written this, because we will try to change many of the C's and check how the solutions change and the trajectories change, okay. So, that is the reason why I wrote all of this, okay. And let us actually pick some point, let us say point 2 comma point 1, okay. So, let the initial point be point 2, point 1. So, I want x1 plus x2 plus x3 as 1. So, it has to be 0.7, and 2x1 plus 4x2 plus x4 should be 3. So, this is 0.4 plus 0.4 is 0.8. So, this is 2.2, okay. So, let me just write down a, b, c and x0 and then leave it to the code, okay. 11102401, A is 1110 and 2401, and yeah, so this is going to be 1 comma 3, and this yeah, this will figure out, but yeah, x is going to be 0.2 comma 0.1, and yeah, so these two are going to be very different, 0.7 and 1.2, sorry 2.2, right, yeah, yes, 2.2, okay. And for C, so I will first write -1 and -half, so the answer should be 1 comma 0. This is -1 and -half, yeah, the other two are anyway 0, okay. And yeah, so here it has to be just x of 0 and x of 1, okay. I will remove x of 2, here as well I have to do that. So that is just for plotting purpose, okay. Okay. And yeah, so here as well I have to change this from 0 to 0.5, you have, so you have this equation, right, 2x1 plus 4x2 equal to 3, yeah, it is a boundary point, so x4 is 0. So x2 will be 3 by 4 minus x1 by 2, right. So 3 by 4 is 0.75 minus t1 by 2, okay. So yeah, this is 1 minus t2 because, so you just have x1 plus x2 equal to 1, okay. So this does not change, and okay, let us see how the feasible set is, the trajectory is, and so on, and note that the answer is 1 comma 0 because we have put -1 and -half, okay. Okay, so there is a problem. Oh, I forgot to put a comma. Yes, okay. Okay, so just to explain what is going on. So you see this blue and orange curve, right. So imagine the x1 axis and x2 axis, right. So those are the boundaries. So you are at an interior point here. So you are, the curve first moves here and then goes down to 1 comma 0, okay. So that is the answer, and of course I mean I could have drawn the other boundaries as well and had these in the same color, okay. Yeah, I agree that what we are seeing here is not like the best representation of the feasible set and the trajectory, but I think it is okay because yeah, I mean it is just for your understanding purpose, as long as you understand it is fine, okay. And note that we started with 0.2 comma 0.1, right. So and then this is the movement, okay, fine. And okay, so let us try a different number, say -1 and -1.5, okay. So let us check what we get out of this, okay. So the answer is half comma half, you know that. So but the trajectory is really weird, so it goes here, it goes here, and there is a small detour here, so it is not straight away coming here, but it comes after a slight detour, okay. So that is why you have 11 steps, maybe slightly higher, okay. And yeah, so you can also try -2.5 where the answer is 0 comma 0.75, right. Yes, okay. So yeah, that is quite a bit of a detour here. It anyway, I think in the first step anyway it goes here whatever happens, and from then on it takes a long detour, okay. It takes 12 steps now, okay. Yeah, but nevertheless you got to the answer 0 comma 0.75, okay. Alright, fine. So yeah, that is one of the examples that I wanted to discuss. Of course you can try by changing C, by changing the initial point, right. So and also observe what is going on with the trajectories and so on, yeah. So I will leave you to play with the algorithm, right, fine. So now we will work out the other examples that we worked in the simplex method, right. So there was one unbounded example that we worked with, if you could recall, right. So we will go to that part, okay. Yes, so this is the problem, okay, where yes, this is the problem, okay. So we are minimizing 3x1 minus 2x2 plus x3 subject to x1 minus 2x3 greater than or equal to 4, 2x1 minus x2 plus x3 greater than or equal to 2, and x1 x2 x3 greater than or equal to 0. So no further plotting because we are working in 3 dimensions now, okay. But nevertheless we will write down capital A, little b, and CC is 3 minus 2 1 0 0, okay. So, A is minus 1 0 2 1 0, yeah. So, this is minus 1 0 2 1 0, and the next one is minus 2 1 minus 1 0 1, minus 2 1 minus 1 0 1, B is minus 4 minus 2, and C was 3 minus 2 1 0 0, okay, yeah. So, 3 minus 2 1 0 0, yeah. So, we have to figure out a starting point, okay. So, yeah, that is a BFS that we have here, right. So, of course, we can write that, but I would like to caution you against this point, okay. The reason is you have a lot of zeros here, okay. So, during inversion it is likely to cause a problem, okay. So, let us first work with this and see what is happening, okay, and then discuss what has actually happened, okay. Yeah. So, from now on we can remove the plot business, okay. Yes, and yeah, so this also can be removed, yeah, this can, okay. And yeah, so let us just try this. So, this will actually give a problem, let us see what it is. So, what it says is, I mean, it has stopped at the first point because this is a problem, because we are at a vertex, right. So, we are not at the interior point, okay. So, I will get a by for the first step, right. So, if k equal to 0, yeah, it goes in any way, okay. Yes. So, you can see that, yeah, the points have become NaN, and the reason is that you are actually dividing by 0, okay. So, as we cautioned, when you invert 0 you always have a problem, right. It is good to avoid zeros as much as possible, okay. So, anyway, we will construct an interior point, okay, in such a way that Ax is equal to B, okay. Okay, so we will try to 1 comma 1 here, I mean, because we are just avoiding 0. So, the next highest is 1, I mean, if you do not consider fractions. So, let me put 1 comma 1, and let us check if we are getting nice numbers here. You need Ax equal to B. So, it is minus 7 plus 0 plus 2 is minus 5. So, when you put 1 you get minus 4, okay. So, minus 7 plus 2 minus 5 plus 1 is minus 4, okay. So, this is minus 14 plus 1 minus 13, minus 1 minus 14, this is 0, and this should be 12. So, that minus 14 plus 12 is minus 2, okay, alright. So, let us check what happens here, okay. What are we getting here? So, you can see that x1, x2, x3 is just off to some very high value, right, e power 175, sorry, that is 10 power 175, 10 power 174, right. So, that is the clue that you get when you have a problem that is unbounded, right. So, the x keeps on blowing up, right. So, that is how you recognize that problem is unbounded. So, right. So, I mean, in simplex method there was some mathematical reasoning how we actually say that it is unbounded, right. So, here we do not have that. The way how you find that it is unbounded, it is just that your solution is actually going to blow up, okay. So, yeah, keep that in mind. So, yeah, I mean, if you want to avoid this unboundedness, you can just modify your C to be minus 1, okay. So, to just give you an idea what is happening. So, recall that 3x1 minus 2x2 plus x3 was blowing up because, yeah, x1 by 2 minus 2 and 5x1 by 2 minus 4 was feasible, right. So, if you do the objective function 3x1 minus 2x2 plus x3, you are getting minus 3x1 by 2 plus 6, right. So, what happens if, so what is 3x1 minus x2 plus x3? So, again you can substitute this, you will have 3x1 by 2 minus 5x1 by 2, right. I do not know if I had written this right, no, yeah, so okay. This was actually the reverse, 5x1 by 2 minus 4 should come in front, yeah, x2 is this and x3 is x1 by 2 minus 2, okay, fine. Yeah, now when you write this down, you will have 3x1 plus x1 by 2 is 7x1 by 2 minus 5x1 by 2 is x1, and this yeah, let us see, so you have minus 2 plus 4 is plus 2, okay. So you do not have a negative in x1, right. So yeah, it is not going to blow up to or go down to minus infinity, okay. So at least for this feasible point, what I had written a few lectures back, I think in week 9 if I remember right, okay, or possibly the first lecture of week 10, okay. So yeah, it is possibly not unbounded, okay. So let us check, yeah, it is not, and the answer is 4 comma 6, okay. So you can see that the other 3 are zeros, okay. So it is 4 6 0 0 0, so it is just 4 6 0, the other 2 are slack variables or auxiliary variables, right. So you have 4 6 0 as the right answer, okay. So yeah, that is one other problem that I wanted to show you. So when you have LP to be unbounded, please remember, I mean this algorithm does not print unbounded, right. So it says, I mean, yeah, the x values blow up, and yeah, so you figure out that, okay, so if it is blowing up, then it is possibly that the problem is unbounded, okay. So that is something you have to keep in mind. And so if you recall the final problem that we worked out in simplex method, it was a pathological example where yeah, I told you that it takes 2 power n iterations, right. So we will work out that example as well, and we will close the examples for the affine scaling method, okay. So yeah, so if you recall, yeah, this is the problem, you are maximizing 2 power n minus 1 x1 plus 2 power n minus 2 x2 and so on, right. So yeah, so this is A, you have 1 many zeros and 1 many zeros and so on, right. So I will just write this down rather than discussing what this is and so on, right. So I will write it for n equal to 3. So you will have a 3 cross 6 matrix A. So you will that will be 1 0 0 1 0 0 and this will be 4 1 0 0 1 0 and 8 4 1 0 0 0, okay. And B is just 5 25 and 125, okay. And C is minus 4 minus 2 and minus 1 and 0 0 0, okay. And X, yeah, we started there with 0 0 0 all zeros, so here we can't do that. So we will start with 1 1 1, not a big issue. So yeah, this is going to be 4 because x1 plus x4 is 5, here it is 4 x1 plus x2 plus x5 is 25. So you have 5 plus 20 is 25, right. So this has to be 20, and here it is 8 plus 4 plus 1, which is 13, 13 plus this is 1, sorry, 13 plus x6 is 125, so that is 112, okay, right. So yeah, we have got all of ABC and the initial point. So let us run the example, okay. So here is the answer 0 0 125 and 5 25 and 0, okay. So that is the answer. So yeah, we have got it in about 25 steps, okay. So yeah, so this is when you have 3 n equal to 3. For n equal to 4, you will yeah, of course will have more iterations, but you will also face a little bit of issue. So let me show that to you. So I am just converting the matrices to accommodate the fourth variable, right. So 16 8 4 1 0 0 0 1 and this is 525 and 125 and 625. You will have a minus 8 in front and a 0 at the end, and okay, so here you have to put one more 1, and here you will have 16 plus 8 plus 4 plus 1 is 29. So, it is 596 plus 29 is 625. Okay. All right. So, let us check what is happening here. Okay. So, the answer here is actually the right answer, right. So, you have 0, 0, 0, 625, 5, 25, 125 and 0, right. So, it is not at 565th step. Okay. So, though it looks like yeah, it has not converged. Okay. So, let me actually show you where it actually converged. Okay. It is not at 500 and whatever. Okay. Yeah. So, in like about 34th or 35th step. Okay. 34th step. Okay. So, you can see that it is 0, 0, 0, 625 and 5, 25, 125 and 0, that is the right answer, right. So, but since you have very large numbers, right, 625, 125, these are all like very large numbers. So, your C transpose mu minus C transpose x minus B transpose mu happens to be huge, though the answer is very, very close. Okay. So, even for very close points, you can see that the distance between C transpose x and B transpose mu is 1.1 into 10 power minus 5 and it never goes below that. Okay. So, yeah, suppose you write say 2e minus 5 for example, okay, you will see that it is converged in 35 steps. Yeah. So, and here is the answer 0, 0, 0, 625, 5, 25, 125 and 0. So, yeah, this is something that you would not have seen in simplex, because I mean the stopping criteria does not depend on the tolerance levels, right. So, that is possibly the only algorithm that I ever know which does not have a tolerance level, right. So, because I mean it traverses the vertices instead of choosing the descent direction and all that, right. So, yeah, that is basically the reason. But yeah, so I mean that is something you have to keep in mind when you are actually running the affine scaling method. Even for other methods, when you are having very large numbers, you might have to rethink on the tolerance. I mean, we did not have an example where that happens, but if you are working on more and more practical examples, you will see many such issues which has nothing to do with the algorithm. Keep that in mind. I mean, it's more to do with the numbers that we are choosing and so on. Okay. So, yeah, this is roughly about the affine scaling method. You can see that, so if you compare it with the issues of the simplex method, right. So, like finding a BFS, you have to find an internal point here, but that is comparatively simpler. Consider finding a BFS and finding an initial point. I mean, finding an initial point could be hard, okay, but not I mean it is comparatively simpler, because I mean if you think of a structure, right, finding a point in the interior can be easier than finding vertices, right. So, finding vertices is a little bit hard, but interior points comparatively are simpler. Okay. And yeah, so there are no pathological examples here which actually I mean derails the whole algorithm or anything of that sort. Okay. So, that there is a proof which says that the worst case is polynomial. Okay. And in practice, affine scaling method works very well as well. Okay. Yeah, but if you want to point out certain issues, of course you can say that yeah, it does not, a simplex method is something that actually tells you that the problem is unbounded, but here it is not telling you such things, right. So, I mean you have to figure out from the answer, and of course finding an initial point has its own challenges, right. Sorry, finding an initial point which is an internal point, right. So, choosing zeros could actually end up in a disaster. So, that is something we have to be very careful. In simplex method, in many cases all zeros would actually work. I mean if all zeros were an initial point, yeah, I mean you can simply start with all zeros and move ahead, right. But here you have to be very careful to not have zeros. I mean choose a very nice internal point, right. So, these are some of the issues that you can point out in affine scaling method. Okay. So, yeah, with this we will complete affine scaling method, and yeah, we will start with a fresh method in the next lecture. Thank you.